All right, in this video, we are going to be moving into section 5.3. So in the previous video, we talked about an introduction to logarithmic functions and talked about maybe a couple of things at the end, like cancellation properties. In this video, I want to dive a little bit deeper into some other properties of logarithms that might be helpful for us as we continue our talks here in chapter 5. So as we move into the properties of logarithms, most of these properties that we're going to cover today are used in the form of either expanding or condensing different logarithmic expressions, especially ones that have more than one logarithm involved. So, kind of reiterating a few things from the last video, as we work with these logarithms today, please note that we are going to end up using bases that are positive because we don't do negative base logarithms. And we're also not going to do a base of 1 just because those get a little bit messy and it's not something we want to dive too far into. Now, for these properties, the u, the v, and even the r, those can be any values. U and v more specifically need to be positive because those are going to be inside of your logarithm, and r needs to be positive, or it can be any real number because those are going to represent constants. So the three rules that you see here on this screen kind of follow along with what they're doing. The first one is called the product rule. So what the product rule for logarithms says is if you have a logarithm where there are two things being multiplied together, that's fine. We can break those apart into two separate logarithms as long as you use addition between them. So log base b of u times v is equal to log base b of u plus log base b of v. So we can use this in an expansion and condension idea, where if you have multiplication, you can break multiplication into addition. If you have two logarithms added, you can put those together as multiplication. Your second property is called the quotient rule for logarithms. And similarly, quotient means division. So if we have a logarithm where two things are being divided by one another, so like log base b of u divided by v, what happens is you can break that apart by using subtraction. So that can be broken down into log base b of u minus log base b of v in this case. Once again, division can break down into subtraction, but also go in the other direction. Subtraction, you can use that to combine into division. And finally, we have the power rule for logarithms, I should say. So this one only has one logarithm in it, but it is a rule that we will see once in a while. So it says, what happens if you have an exponent inside of your logarithm? So something like log base b of u raised to the r. Now, in the previous video, we talked about that if the base and the number next to it match, they just canceled. But obviously, b and u are not the same thing, so they're not going to cancel here. So when they don't cancel, how we will deal with that in this class is we can take our exponent r, and it can be brought to the front, and you can rewrite it as r times log base b of u. Because most of the time we don't like having an exponent inside of our logarithm unless we really, really have to keep it there. So typically we will bring that exponent to the front and write it as a constant. Now, once again, you can also go the other direction if you're trying to combine logarithms. If you have a number in front of a logarithm, you can always bring it back inside, but remember, it will become an exponent of the base u that's already there. And so there are there's at least another one or two properties later on in this video, but for majority of this video, these are the three properties that we're going to focus on. So let's look at some examples. So over the next few examples, what I would like you to do is take these logarithms, and I want you to use the properties of logarithms to expand each logarithmic expression as much as possible. On certain parts of the problem, you may be asked to evaluate it, and we're going to do that without a calculator because we don't want decimals, we want exact answers. So for example, on number 1, you have the natural log of 5e squared. Now, from the properties that I've just discussed today, what I notice is that inside of our natural log, which is a logarithm, you have two things being multiplied together. So if you're trying to expand this, the product rule of logarithms says multiplication can be broken up into addition. So I can rewrite this as the natural log of the first term, which is 5, plus the natural log of the second term, which is e squared. Now, from these two terms, you need to double check, is there anything else you can simplify? And actually there is. Natural log of 5 is not something you can mess with, so I'm just going to leave that term alone. But if you remember back from the previous video, if you ever have a natural log and an e next to each other, that was one of our properties that says they will end up canceling and you'll just have the exponent left over. So since the ln and the e cancel, they go away, and the only number that is left over is the 2 in the exponent. And so your simplified answer becomes the natural log of 5 plus 2. Now, in my second example, we have a log base 2 of m divided by 32. So in this one, instead of two things being multiplied together, we have two things that are being divided. So from our quotient rule of logarithms, anytime you're dividing two terms, you can break that up into subtraction. So I would write this as log base 2 of the top, which is m, minus log base 2 of the bottom, which is 32. Now, when you look at both of these terms and asking yourself, can you simplify them any further? The first one you cannot. Since log base 2 of m has a variable in it, it's not something that I can simplify any further. But this log base 2 of 32 is something that we talked about in the last video of how to simplify. So let's remind ourselves how we did that. When we had a log base 2 of a number, or log base number of another number, we would set this equal to x, and I would have y'all rewrite this as an exponential equation, where you would take the base, which is 2, and if you remember, you have to flip-flop the two values. So the 32 would go over by itself, and the x would come over to become the exponent. And then if you ask yourself, 2 raised to what number is 32, you would find out that 2 to the x, or you can rewrite 32 as 2 to the 5th. Either way you do this, you can find that x would end up equaling 5. Since that is the value of this logarithm here, when I come back to my purple and write my final answer, I can replace log base 2 of 32 with its exact value, which is 5. And that would be as far as you can go with the simplification of number 2. All right, let's do one more like this. This one's got a few steps in it, but same thing. I want you to expand this single logarithm as far as you can and simplify and evaluate when necessary. So we have the log of the square root of x divided by 100y cubed. All right. So the first thing I notice, at least the overall big thing here, is that you've got division inside your logarithm. So just like number 2, I'm going to break up this division into subtraction. So it will become the log of the top, which is the square root of x, minus the log of the bottom, which is 100y cubed. Now that you've broken up the division into subtraction, you might notice that there's something else you can also break up. Inside of your second logarithm, you now have two terms that are being multiplied. So similar to problem number 1, we know that we can break multiplication up into addition. So I'm going to do that on the next step. This would become the log of the square root of x minus, and you're going to have the log of the first number, which is 100, plus the log of the second term, which is y cubed. And you might notice that I put this inside of brackets. You can also use parentheses here. I did that because since you're picking up multiple terms, you're going to have to subtract all of these in just a second. So that's why I did that. So now, one thing or I guess two things I'm going to go ahead and talk about while I'm here. Number one is the square root of x. We don't like to leave square roots either inside of logarithms. So you might remember from our talk about radicals or from your previous knowledge of algebra is that the square root of x can be broken up, or sorry, rewritten, I should say, as x raised to the 1/2 power. So I'm going to go ahead and take care of that while I'm here, and you'll see why I'm doing that in just a second. Minus, open bracket, inside of the bracket, while there's nothing you need to do with the log of y cubed just yet, you do want to go ahead and simplify the log of 100. So coming back over here to the right, I kind of out of the way. If you're being asked to evaluate the log of 100, once again, log and 100, there is no variables there, so we can set that equal to x and solve. And so you would start with the base, which remember from the last video, your understood base is 10. The number next to your logarithm goes to the other side, which is 100, and the x comes to the left and becomes the exponent. And so if you were to rewrite your left-hand side, we should know that 100 is written as 10 squared. And if you just set the exponents equal to each other, you can say that x is 2. So we can replace this log of 100 with a single value because I was able to simplify it. So this log of 100 will become 2, and then you'll have plus the log of y cubed. The next thing I'm going to do is distribute the negative to both terms. So you'll have the log of x to the 1/2 minus 2 minus the log of y cubed. Now, don't stop here. A lot of students I've had in the past would stop right here and they wonder why the homework marks them wrong. From the rule that we don't use very often, the other thing we don't like to have with our logarithms is exponents. So anytime you end the problem and you've got exponents inside of your logarithm, you want to get rid of those. And you can do that by bringing the value to the front of the logarithm with respect. So on that first term, I'm going to bring the 1/2 to the front and write this as 1/2 the log of x minus 2. And then on the third one, I'm going to bring that 3 to the front and write it as minus 3 times the log of y. And this is your simplified, or I guess most simplified form of an expanded logarithm here. And so I also like this problem because it uses all three rules. We had to use the product, the quotient, and the power rule of logarithms within one problem. So that's your example of how to expand logarithms, or I guess you'd say 3 examples. Now I want you to be able to go the other direction, which I think students actually like better. So maybe you'll agree with me, or maybe you won't by the end of these problems. But what I would like you to do is to take these multiple logarithms and I want you to put them together using your rules that we've covered so far in this video. So on number 4, you have log base b of x minus 7 plus log base b of x. Well, when you're condensing, you have to see what's happening between your two logarithms. In this case, these two logarithms are being added. So going back to our rules that we've learned, when two logarithms are added together, you put them together with multiplication. So this becomes log base b of your first term, which is x minus 7, multiplied by your second term, which is x. And then from there, what you can do is you can multiply these together. So I would distribute that x through, and you would get log base b of x squared minus 7x. This is your fully condensed answer. You can't go any further than that right there. Moving over to number 5, you have 2 times log base 8 of m minus 1/3 log base 8 of n. Now, you might remember from the last problem in the last section, or in the last part of this video, is that typically when numbers are in the front of logarithms, that means you're going to have to use your power rule. Now, we're going backwards, so the numbers are already in the front. What we're going to do is anytime we have a number in front of a logarithm and we're being asked to condense it, you're going to bring it back inside of its respective logarithm. And remember, it becomes the exponent of what's inside. So you would actually be left with log base 8 of m squared minus log base 8 of n to the 1/3. Now, m squared can't be simplified anymore, but n to the 1/3, we've talked about that a few times now in these videos. You can rewrite that. So we'll have log base 8 of m squared minus log base 8. And remember, n to the 1/3 would be the same thing as the cube root of n. So now that I've simplified what's inside the logarithm, now my attention turns to what's between them. These two logarithms are being subtracted from one another. So from our rules that we've learned in this video, subtraction means you can condense them with division. So this would end up becoming log base 8 of the first term, which is m squared, divided by the second term, which is the cube root of n. And this is your fully condensed logarithm for number 5. All right, and just doing one more before we go to the last topic in this video, let's do one that has 3 logarithms in it. So we've got 1/2 the log of x minus 1 minus 3 log of z plus the log of 5. I would like you to condense these into one single logarithm. So using our knowledge from the first 2 problems we did, the first thing I notice is that this logarithm has a 1/2 in the front and this logarithm has a 3 in the front. So just like the previous example, I'm going to bring those inside their respective logarithm and they become the exponent, all right, of each one. So we're going to end up doing the log of x minus 1 to the 1/2 minus the log of z cubed plus the log of 5. Now, z cubed can't be simplified any further, so I'm not worried about that term, but that first term, excuse me, x minus 1 to the 1/2. Similar to the last problem where we said the 1/3 power would be a cube root, anytime we see a 1/2 power, that's the same thing as a square root. So I can rewrite that first term as the square root of x minus 1, while everything else will remain the same. And now, just like any good problem, I'm now going to work from left to right. So the first thing I notice is that our first 2 logarithms are being subtracted, so I can combine those with division. So this would be the log of the square root of x minus 1 over z cubed plus the log of 5. And now I have 2 logarithms that are being added together. So we've learned that when they're added, you can multiply them together. And so this will give you a final answer of the log. So if I multiply, that would be 5 times the square root of x minus 1 over z cubed. And that would be your fully condensed logarithm. And so over the last 6 problems, we've now seen how you condense and expand logarithms using just 3 simple properties that show up a good bit in these ideas. The last little thing I want to show y'all before we wrap up this video for section 5.3 is one more property, and it's called the change of base formula. All right. So when you are working with a logarithm that doesn't simplify very nicely, we'll see some of these in the next video, we have a way to approximate this or to write it in a different way. So as you can see in my box, and this is a formula you have to memorize for your assignment, for your test. If you have log base b of u, and we don't know how to simplify that, so we try to rewrite it, it doesn't come out very pretty, so we can't do anything with it. What we can do instead is we can rewrite this using natural logs. So we can rewrite log base b of u as equaling the natural log of u divided by the natural log of b. So we will only use this on logarithms that either request it or the ones that we can't simplify very nicely. So let's move down to these two problems here and let's wrap up this video. These instructions say use the change of base formula and a calculator to approximate the following logarithmic expressions and round your answers to 4 decimal places. So on number 7, you have log base 4 of 59. So that's not a logarithm that comes out to be very nice. So as you'll notice from our previous problem, we can rewrite log base b of u equal to the natural log of u over the natural log of b. So when I'm asked to simplify the log base 4 of 59, I can rewrite this as the natural log of the number inside, which is 59, divided by the natural log of your base, which is 4. And from here, you're going to have to just get your calculator out and approximate this. So if you want to pause the video and try yourself, you can. But I'm going to do the natural log of 59 divided by the natural log of 4. And if I have to round this to 4 decimal places, this would be 2.9413. And that is the approximate answer to number 7. Just to do one more so you have it in your notes, let's approximate what log base 7 of 47 is. So using the same change of base formula, I can rewrite this as the natural log of the inside number, which is 47, divided by the natural log of the base, which is 7, and then I can use my calculator to approximate this to 4 decimal places. So let me do that. Natural log of 47 divided by the natural log of 7 should end up being, to 4 decimal places, 1.978. And the next number on my calculator is 5, but there's an 8 after that, so that will round it up to 6. So it is approximately 1.9786. And so that's how we can use the change of base formula to get approximate answers of logarithms that aren't very nice to work with. So that wraps up section 5.3 in our continual talk about logarithms. In this video, we covered 3 major properties: the product rule, the quotient rule, and the power rule. And then we also discussed the change of base formula. In the next few videos, we're going to tackle one of the longer sections in this class. We're going to look at section 5.4. So while in that section, there are 3 different types of equations that we have to solve and be able to work. So what you're going to notice in the next section is that I'm going to make 3 separate videos for section 5.4. Each video will cover a different technique of how you solve different kinds of equations.